going on. And so I want to start by talking about a straightforward application of electroosmosis that's particularly relevant to microfluidic devices, and that's called an electrokinetic pump. It's perhaps the most basic example of the Couette flow, the surface-driven flow, combining together with the pressure-driven flow, the Poiseuille flow, in a specific context that highlights what the differences in scale do, and what simultaneously highlights how, once we take these terms and put them into this electrokinetic coupling matrix, a bunch of stuff gets a lot easier. OK, so let's talk about an electrokinetic pump. Let's suppose that I have a glass capillary. Glass capillaries are easy to buy. If I buy a glass capillary, let's say it has a diameter of 50 microns. And if you buy a few silica glass capillary that's 50 microns in diameter, this might cost something like $5 a meter. Now, I want to use this capillary to create a pump. And what I want to do is I want to put voltage in at one end, and I want to get pressure at the other end. So I'm going to fill this glass capillary up with fluid. I'm going to put one end of it in a reservoir. I'm going to take the other end, and I'm basically going to close it off. But I'm going to do so in a manner that allows me to apply a voltage across this system. So I have a glass tube that I just bought. I filled it with some salt water. I stuck one end of it into a little dunk tank that has some more salt water. I closed off one end, and I applied a voltage to these two ends. And the most common way to do this is by connecting both ends to a platinum wire. Now, when I apply this voltage, what do you expect will happen at the end of this device if I connect this to a pressure transducer? Well, I could, in theory, measure a current. I don't have an ammeter connected up to it yet, but I could, if I assume that this is now a voltage source, I could connect up an ammeter in series with that. And if I did this, I would, in fact, measure that there was a current. So I have a current. Actually, yeah, I may have misunderstood your comment. Did you mean a current through the device, or do you mean a current from the pressure transducer? Sure. Yeah. So let's not focus on the details of how we'd read out the pressure transducer, but fundamentally, the pressure transducer will measure a pressure, right? And will that pressure go up or down? Pardon? Why will it go up? How would you know that the flow goes towards the closed end? Okay, so in particular, we need to specify the polarity of the electric field that's established by that voltage. So let's now be more specific about that and say that this electric field is in fact positive in the direction of from inlet to outlet. If the electric field is pointing in this direction, that means that the negative gradient is pointing in this direction. That means that I have a high voltage here and a negative voltage there. So I've connected up my power supply. I made the voltage high here and the voltage, relatively speaking, negative there. If that's the case, if my capillary is assumed to be negatively charged, and that will be the case for a glass capillary at some moderate pH. Then my pressure is going to go up. By how much will my pressure go up? Will it be linear with the applied voltage, or will it be nonlinear with the applied voltage? We have 1 vote for nonlinear. Do we have more votes for nonlinear? Do we have more votes of any kind? Do we have votes for the bunny? He's still hanging out with me. He's on the table. I have one vote for linear. So now I have 1 vote for linear and 1 vote for nonlinear. Yeah?
Well, you're going to have a current, a flow.
That's right.
Electric field.
Yep.
Right, but you're going to have a pressure. You're going to have missile flow going the other way.
That's right. Yeah, I'm going to have an electroosmotically induced flow in one direction and a pressure-induced flow in the other direction. Will those be, which one will be higher? Will my electroosmotically induced flow be higher, or will my pressure-induced adverse flow be higher?
Well, they should reach a steady state.
Yeah, they have to reach a steady state where they're equal. In fact, we can think of this closed end, right, as being a specification that Q over A equals 0 in this system, right? I can't have any mass coming out the end. Conservation of mass says that the amount of mass coming out this end has to be the amount of mass coming in at the inlet, and in fact the amount of mass moving in every region along this tube, right, if I assume the flow is unidirectional. So this means that the average velocity across every cross-section, in fact, is 0. And so I have a voltage that's generating an electroosmotic flow that's moving from inlet to outlet, but I have to have a pressure-driven flow that's pushing the fluid back from outlet to inlet, and in fact the integrated magnitude of both of those flows has to be identically equal at steady state. How long will it take for this system to come to steady state? Very quickly is a good answer. It will come to steady state very quickly. Yeah, so the key thing, if we want to measure the finite time for the system to come to equilibrium, we have to factor in the compliance. If we don't have any compliance in the system is rigid, the system will almost instantaneously come to steady state. Within the approximations we're using of these equations, it will come to steady state instantaneously. In fact, there is a finite time for things to start up, etc. And if this system has a bunch of compliance, then there's going to be a finite time required to bring this to equilibrium, which is going to be proportional to both the hydraulic resistance and the hydraulic compliance. So let's draw the picture of what's going on inside this channel. Yeah.
So I'm a little confused about the diagram that you've drawn for the electrokinetic pump. Can you just better define the internal pressure transducer? Because what is that end physically? So at one end I have a reservoir where I've applied a lot of plasma electrode applying the potential with respect to another reservoir, right, where I have the same electrolyte with the same solution and another plasma product. So that end is connected to a pump. Is that
So the question is maybe like physically how I'm establishing these boundary conditions. So we can talk about what a mathematical statement of the boundary conditions are, and then we can talk about physically what this corresponds to. So here, the fluid mechanical boundary condition is that the pressure is equal to the pressure of the ambient pressure of the lab, and the voltage here is higher than the voltage at the other end by something specified by the voltage. Over here, the boundary condition is specified by saying Q over A is equal to 0. And then the pressure will come to an equilibrium pressure, which I'm now measuring with my pressure transducer. So the pressure transducer is meant to be a measurement. In terms of like really in the lab how I create these boundary conditions, here I have a reservoir with some salty water, and I stick in a platinum wire to define the voltage, and I stick in a glass tube to allow for there to be a fluid mechanical connection. If I describe what's going on at the rightmost end, this is now a little bit trickier. In the lab, I would have to do this with a fixture. And so if I zoom in to the fixture that I would have there, now I have my capillary, which I've drawn really big. And typically, I would put this into some sort of fixture. And so a simple example of what a fixture might look like is a little piece of plastic where I can screw in a bunch of things, 2 or 3 or 4, as is I've drawn it for 4. I need to connect up a platinum wire, and so I've screwed in a platinum wire in one end. In another end, I've screwed in a connection that's going to a pressure transducer. And then I have a fourth output, which in this case I wouldn't need. And so if I had a 4-port connector, I would connect a platinum wire in one of the outputs, my capillary input in another one. This would be another tube that would go to the pressure transducer, and I'd have one extra, and I would just put a plug in.
This is all same electrolyte.
So the electrolyte is throughout this tube. This electrolyte needs to be filling this enough to make electrical contact with this platinum wire. The plug doesn't matter. This electrolyte bath is presumably then continuing through here and connecting to the pressure transducer, because I'm using a pressure. The pressure transducer doesn't really care about whether it's liquid or solid, but in this case, this would be a pressure transducer designed to work with liquids. Is any of this helping even the slightest bit?
Yeah, it does. It creates a big difference for you had with the next.
Yeah, with my, yeah. It was a conceptual drawing.
Yeah, it makes much more sense.
Cool. Other questions? Okay, so now let's zoom in. Let's zoom into this channel and see what's going on. And in fact, we'll talk about the flow in this channel chronologically. And in fact, this chronological description really depends on there being some finite compliance in the system. It turns out realistically, if you connect this system, it always has a finite compliance. And what I'm about to describe typically will require at least a second or two at minimum. Okay, so I have a tube. I start out by applying an electric field, as denoted by the green line and the platinum wires. When I do that, I generate an electroosmotically induced flow. That basically looks like this, right? Now this flow has a net mass flux, which means that the flow starts moving from left to right, right? That can't be consistent with the fact that I have a closed end, right? So this is only sustainable if I have some finite compliance in the system. If I have a bubble that I'm compressing, if this capillary is stretching out a little bit because of the increased pressure. Pretty quickly, this system goes to equilibrium. Well, how can the system go to equilibrium, or more precisely, steady state? Well, somehow, the net mass flux that I see in this flow has to go to 0. So it can go to 0 if the electric field goes away, except it doesn't, because I'm controlling the electric field with my power supply. So what has to happen? Well, there has to be a counteracting pressure-driven flow. So as this is flowing, the compliance of the system is taking some out of this extra pressure, or this extra volume, filling the system up. The net effect is that this pressure at this end is increasing. I'm increasing the pressure at the downstream end. I'm not increasing the pressure at the upstream end. That's connected to the environment, right? So this pressure starts to increase. As this pressure starts to increase, now there's an additional component on this system. Now I have a pressure-driven flow drawn horribly. Interestingly enough, still drawn horribly in my second attempt, but at least the boundary conditions were closer to being correct. This pressure goes up, I start having a pressure-driven flow. And in fact, if I superpose these two components, and I should be clear, these two components are not separated spatially. I'm just drawing them separately so that you can see them. Everything is going on simultaneously at all parts in this channel. If I superpose this and this, I get something that looks like that. Now, can this be my steady state solution? No, why not? I still have a net flow, right? So this is what I'm going to see as the system starts to build up pressure, right? In fact, if I go more time, this pressure continues to increase. The pressure gradient continues to increase. This pressure-driven flow starts to look more like this. And then my superposed flow starts to look more like that. And when I get to the point where the integrated volumetric flux goes to 0, right, when the fraction of this that's going forward is canceled out by the fraction that's traveling backwards in this flow, that's my result when I get to my steady state solution. So in fact, if I take this glass capillary and I apply this voltage, several different things happen. I build up a pressure at the outlet, which I can measure at my pressure transducer. I generate a flow that moves forward near the boundaries, but moves backwards in the center. And in fact, if I extend out the streamlines of this system all the way from the inlet to the outlet, my streamlines all look like here in the center of this tube. Again, I said that my velocity distribution looked a little bit like this. I have flow moving on the outside, dominated by the electroosmotic flow, but there's a pressure gradient, and that pressure gradient dominates on the inside, pushing this flow back. This velocity distribution in the middle of the tube is described by our unidirectional flow equations, basically just a sum of a uniform flow caused by electroosmosis minus a parabolic flow given by the pressure gradient. How about this? I mean, as I've drawn it here, this says that when I close the end and connect it to a pressure transducer, this fluid that's moving here at the top has to turn around. How is this described by the equations that we've written so far? I do have a non-zero pressure gradient. How does that combine with the equations I've written to describe what happens when the streamlines are turning around? Yeah. Oh, just stretching?
I think that when we get to the very end of pressure goes up a lot, and then we look at that the pump equation, and then P over A, that pressure gradient will actually be negative in that direction, that will turn around. Right? Usually like that phi, delta phi angle. So that will actually counteract that effect of that potential.
There is an adverse pressure gradient, and in fact there is an adverse pressure gradient everywhere. And that adverse pressure gradient in its own way affects the velocity here and here and here and here. In fact, everywhere across this channel, the adverse pressure gradient affects it. In the center, the adverse pressure gradient is dominant. At the edges, it's not. The key thing that's different about what's going on over here is that the flow is not unidirectional. Every thing that we've done in our analysis is unidirectional. So our analysis describes all this stuff going on in the middle really, really nicely. It, in fact, does not describe the detailed nature of these streamlines at the edge at all. And I mostly don't care. The reason why I don't care is because this drawing is horribly not to scale. Like the length of this, you want to make an electrokinetic pump out of a capillary. That capillary can be a meter long, no problem, right? But its cross-sectional, or its diameter, as I specified, was 50 microns, right? So this thing is actually this really, really huge long thing. This is an edge effect. If I wanted to figure out exactly what the flow was here, I can put it into a numerical solver, and I can solve it, and it's pretty straightforward. But I don't bother doing the analysis for it, because it doesn't really affect any of the key outcomes of the system. What's really important is the relative impact of the surface-driven flow and the pressure-driven flow. Okay. Well, if I want to figure out how much pressure is generated, especially how much pressure is generated per volt, what's a sensible thing to do? Well, an easy thing to do would be to first solve for the velocity distribution, do an integral of that velocity distribution in space. That, by definition, will have an unknown parameter in it, which is the pressure gradient. Integrate all of that, say that that net volumetric flux has to be equal to 0. Solve that being equal to 0, and in so doing, one will find the pressure gradient. And, straightforward, and it's algebraic, and you just do the integral. But it turns out that even though that's a very tractable problem, we don't even need to do that, because the answer comes straight from the electrokinetic coupling matrix. As is, I'm concerned only with the flow, and I'm not paying attention to current, so really I just have one equation. Q over A is given by RH over 8 eta times the pressure gradient, minus epsilon phi naught over eta times the potential gradient, or the electric field. And to find out what happens in this case where I've set QA equals to 0, really just requires that I set Q over A equals 0 in this expression. Now, if I want to arrange this in terms of the pressure I expect to get per voltage, I can take this pressure gradient and say that this is delta P over L. And I can say that this, to be precise, the negative pressure gradient is given by negative delta P over L. This is given by negative delta V over L. These signs, it turns out, don't matter because they cancel out no matter how we define it. And all I have to do is rearrange this to get that delta P over delta V is given by 8 epsilon phi naught over RH squared. And so this says, if I apply voltage to a system and I want to say, well, what's the multiplicative factor that tells me how much pressure I get per volt I apply, it's just given by this. It's proportional to the electrical permittivity of the fluid, proportional to phi naught, inversely proportional to the hydraulic radius. Why is the viscosity not there? Viscosity affects flow. Why doesn't viscosity affect this? That's right. It's not really describing a feed. I use pressure to apply a body force. I use voltage to apply a body force. Both of those forces relate to velocities through the viscosity. But this is just a ratio of two different forces, right? So if I made an electrokinetic pump with honey, it would take really, really long to fill up the mechanical compliance of the system as compared to the one with water. But my final delta P over delta V is always going to be the same, right? So there's nothing here has to do with velocities. Viscosity is not here. The electrical permittivity is here because if I have a material with a very low permittivity, like the real force I have to put into the system to get a voltage isn't very high. But with something like water, I have to put a really big force into the system to get that electric field to be of a specific magnitude to get this voltage, right? So an electrokinetic pump that I run with water is going to be 40 times more effective than one I run with dodecane or something like that. So if you want to make electrokinetic effects important, you want to use, at least interpreted as a function of voltage, you want to use a fluid that has a high electrical permittivity. So high electrical permittivity makes this happen. Viscosity doesn't matter. Interfacial potential matters, right? If my interfacial potential went to 0, I would have no electrokinetic effects, no pump. If I change the sign of the electrokinetic potential, what happens? What happens in this system if I change the sign? A couple of people talked at the same time? Right, it should go to the other way, and then what would happen? I add the flows, and my pressure at the right end does what? It goes up or goes down? It goes down. And so, whereas when I run it forwards, I can crank this pressure up really, really high. All I have to do is make my voltage high and make my radius low, and I can generate a really, really high pressure. I try to run it in the other direction. I run it a little while, and then the fluid cavitates. There's no way for me to generate a large negative pressure in this system. In theory, one can make a large negative pressure with water, but in practice, it's very difficult to do. So I try to run it the other way. This pressure will go down until the fluid starts cavitating, and then I'll just make bubbles. If I run it forward, I can crank the pressure up. This pressure I generate is proportional to the supplied voltage, permittivity, interfacial potential, and importantly, this is inversely proportional to the hydraulic radius squared. And this is the same conclusion we came to at the very beginning when we talked about Couette flow and Purcell flow. I said the surface-driven flow doesn't scale with the characteristic length, but the Purcell flow scales with the length squared. Now if I ask Couette flow and Purcell flow to be in equilibrium, if I say they're going to generate the same flow rates, then the only way for that to happen is for me to have a pressure whose magnitude relative to the voltage is also scaling with this radius squared, right? And so this means that if I take a big, meter diameter glass tube, right, and I say, yeah, electrokinetic pumps work, I'm going to get a big meter diameter glass tube, I'm going to connect it to a high voltage power supply, awesome, right? My flow rate's proportional to the area, so I get tons of electroosmotic flow rate, super awesome. And then what pressure will I generate? Nothing, basically, right? Not any more than someone at one end sort of going and blowing on it can cancel out, right? So if you look at flow rate of electroosmotic flow, the flow rate of electroosmotic flow gets bigger and bigger as it gets large. But who cares? Because the flow rate associated with pressure is going up by the characteristic length to the fourth power, right? I go down to something smaller and smaller and smaller. Yeah, my flow rates are going down. But the relative magnitude of the surface-driven flow as communicated by this voltage and the pressure-driven flow as communicated by this pressure drop, these are not in balance. So I take my device, I make it smaller and smaller and smaller, and pretty soon I find I can get a high-voltage power supply powered by a battery, and I connect it up to a glass tube that's connected to salty water, and I can generate 100,000 psi. Like, no problem. You got to wait around for it to pump up because there's some mechanical compliance in the system. At those pressures, the water's compressible enough to have a finite compliance. But this is a very, very, very simple illustration of how length scale comes into these things.